this is the error at that point. So if we want to minimize the error, what do we have to do? Ideally, what would the error be? 0. So let's set this thing to 0. All right. And then let's basically bring this part over to the other side. So let's write this as m x sub I plus b equals y sub I. Okay, that's setting the error equal to 0. All right. So this is true if we have 3 points, we have 3 equations. mx1 plus b equals y1, mx2 plus b equals y2, mx3 plus b equals y3. This is a system of linear equations. And we can write this then in matrix form. So we can put a 1 in front of each of these, and we can write this set of equations as 1, 1, 1, x1, x2, x3, b, m, and then we've got y1, y2, y3. All right? So, in this case, we're going to call this the model vector, just like we talked about last time. This is actually the vector of parameters that describes the model to which we are fitting the straight line, or the model of the straight line. Now, there's no reason that that model has to be a straight line. Right? It can be anything we want it to be. It's a model of the data. We are modeling the data. Yeah. You're right. Good point. Yeah. Actually, would it be? Actually, in here, I'm sorry. This should be like this. Okay. So it is mine. Okay. So we are simply modeling the data in this thing. So this we're going to call the data vector. And we can think of this in general as model transforming, let's have a black box here, the data. And there's some kind of black box that takes the model of the data. In this case, we're going to pre-multiply m by g, where g is this matrix right here. So pre-multiplying m by g takes us from model space to data space. All right? And like I said, this model vector doesn't have to be 2 parameters. It could be 1. Right? It could be just b. I could change this equation right here. And instead of fitting a straight line to the data, oops, sorry. There's one up here. Instead of fitting a straight line, what could I fit to the data? Well, I could fit a constant. What would the constant be in our parameter frame? What am I how does that change? You know, I've still got the same points. How does that change this equation? Well, m is now 0, right? M equals 0. So I don't need m. I've only got one parameter that describes it. Well, if I don't need m, I don't need the x values. Right? So now all I have is 1, 1, 1b equals y1, y2, y3. Right? Some model, some intercept fits each of those points. Anybody have any idea what b is? If I try to minimize the squared error to find the solution. Remember, what I'm going to try to do is minimize this error. So what do I have here? I have y predicted. What's the predicted value of y? Exactly, it's the mean. So the mean is actually the best least squares fit, or the minimum squared error fit, of a constant to a series of points. But it's simply a model of the data. The mean is a model of the data. If I have a lot more data, I can fit a parabola or some kind of more complicated polynomial. But in general, all I'm doing is fitting a model to the data. And really, when we talk about geophysics, again, we are basically taking a presumed model of the Earth and transforming it to data space through the act of collecting data. And if we make data measurements, that's what we've got. Okay? Now somehow we have to go backwards to the model space. And oftentimes the way we do that, if we have g dot m equals d, is we find that the model is equal to g inverse of d. Now it turns out that if we have an overdetermined system, that g is not square, and so we have to basically do some machinations. So I'll just say approximate in this case. We've got to find a way to calculate the inverse, or we do something more sophisticated to calculate the model. Okay, so that's really what I wanted to talk about in terms of formulating problems as matrix problems. I'll do one more example, and also how model and data are related. A really simple example of regression. Okay? But we can extrapolate least squares regression to almost any type of geophysical problem, or any problem where we have more data than we have model parameters, an overdetermined system. So when you think of it abstractly in terms of linear algebra, you don't really get the value of the technique. You know, you just say, well, I'm fitting a straight line in statistics, right? That's where you learn it. But think about it in a very abstract way. Let's suppose that I make a bunch of ultrasound measurements in the body, right? And what am I really doing there? Well, I'm basically transforming some kind of estimate of what the bone structure or whatever I'm trying to calculate, whether it's the presence of cancer cells or whatever. There's a transformation from the model space, which would be the body in some sense, or some parameter of the body, to the measurements that I get. It's a very powerful way of thinking about just about any problem where you've got data to look at. Okay, on derivatives. I said we wanted to look at how we would form a derivative. Now, when you first took calculus, how did you learn to define a derivative? Remember the very first equation that you had? How did you define? Right. You did the limit as delta x goes to 0 of f this gave us a lot of, and this is f prime of x. It turns out pre-computer, this was the way to do it, right? You could abstract very digital problems to understanding derivatives. Well, now that we've got computers, there isn't as much need to do this. We can actually look at this in a different way. We can say for delta x equals epsilon, some small number, calculate